Okay, hello. You should see the desktop and you should be able to hear me. Does everything seem to be working?
Yeah.
Yeah, okay. Let me get the chat window up. Okay. Um, so first of all, the first programming assignment is available now. It's been up there since yesterday evening. So we'll talk about it in a minute. Okay, it's based on some stuff that we'll talk about today. Okay, so we're going to continue working with these examples in this B tree folder. And probably today we'll finish what we're going to talk about in terms of talking about the tree data structure. So I think today we'll finish talking about the tree data structure, and then we'll turn to the chapter 1 and chapter 2 of the reading in the textbook. Okay, so I've got the binary tree downloaded. Let me unzip it. Okay, now, oh, let me delete the zip file because I don't need it. What I want to talk about today is more examples of doing recursion, because that's what your homework assignment is. Your homework assignment is to write some recursive functions that print out a tree. So you're going to write out a tree in a couple different ways using a recursive function. So let's just go back, and we've done some examples of recursion. We're just going to do some more, and we're going to talk about this file here that has what's called the traversals in it. Okay, so let me open up the B tree. Okay, now remember, the tree is a recursive data structure because a tree is made up of a left tree and a right tree. Okay, so a tree is made up of trees. Okay, so that gives you recursion. The name of the data structure is used to define the data structure, or using another way to put it is the name of the data type is used to define the data type. So this is a recursive data type. Okay, then you process recursive data types almost always by writing recursive functions. So you remember the example we had down here? If you want to know the depth of a tree, the way you find out the depth of a tree is that, well, first of all, if the tree is got a left branch, you want to know what the depth of the left branch is. If there's a right branch, you ask what the depth of the right branch is, and then you take the maximum of those two. The depth of the tree is the maximum of the depth of the left and the right branch. Okay, so that's an example of recursion. The depth of a tree is, you ask the left tree how deep are you ask the right tree how deep are you, and then that gives you, and you actually add 1 to those results. Okay, so the depth of the whole tree is 1 more than the maximum depth of its left or right tree. Okay, another example was, if you want to know the size of a tree, by size I mean how many nodes are in a tree. If you want to know how many nodes are in a tree, you ask how many nodes are in the left tree, how many nodes are in the right tree, and then you add 1 to that, to add 1 to the sum of those, because there's one. This is this accounts for the root node, then all the nodes on the left and all the nodes on the right together, they give you all the nodes. Okay, so you're calling that function is called inside that function, and that function is called inside that function on the parts of the tree that are the recursive parts of the tree. Yeah, you call the on the left tree, you call the size function. So you're recursively calling the function on the part of the tree that is the recursive part of the tree. Okay. And then a third example that was toString. I want to convert the tree into a string. And you do that by converting the root to the root element gets converted to a string. And then you say, okay, now left, convert yourself to a string. and write convert yourself to a string. So the toString method is called recursively. Okay. Now let's do another one. Let's write one. Uh, an important idea in binary trees. We're not going to need it in this class, but an important idea is what's called a full binary tree. Okay, so let me draw a picture. Okay, a full binary tree is when a tree has always has, if there's a left branch, then there's always a right branch. You never have just one or the other. Okay, so we have trees that look like the following. You could have a root, okay, and then you can have a left child, okay, and then that left child can have, say, a left child and a right child. So this is not a full tree. This tree has a left branch, and then that left branch has a left branch and a right branch. And then this right branch is empty, okay? So that would be a tree that if we wrote it out, it would look like the following. That tree would be, actually, let me put something in here. So let me put the number 1 in here and the number, say, 2 in here and the number 3 in there and the number 4 in there. So if I wrote that tree out, it would look like this. It's 1 with a left child of 2, and 2 has a right child of 3, a left child of 3, and a right child of 4, and 1 has an empty right child. Okay, so that's what that tree looks like. Okay, that's not what we call full. To make a tree full, you don't have any empty branches. Okay, so on your, if I do this to this tree, if I give it oops, where, and I've lost my there. Okay, now this is what we call a full tree. Okay, that node has 2 branches. That node has no branches. That node has 2 branches. Every node is either got 2 sub branches or no sub branches. Okay, so then that would be what we call a full tree. Okay. There's also another notion of what's called a complete tree. This tree is not complete because it one side is deeper than the other side. Okay, so if I actually then go and give this thing 2 children, now it's a complete tree. Oop. This one's a complete tree. Okay, a complete tree has there. I'm very sure, right, best way to describe it. A complete tree has 2 to the n children, where n is the depth of the tree. So this tree, this part up here would be a complete tree with depth 1, and this is a complete tree of depth 2. And notice it's got 4 children at the bottom. Okay, so a complete tree, you can see everything is there in a sense, but a full tree is just when it like that. In a full tree, if you've got a child, if you've got a child, then that child is either a leaf node or that child has 2 nodes. Okay, now if I go now and put a node over here, if I put a node here, now that's not a complete tree anymore because this one's got an empty left branch. So let's write a function that asks a tree if it's complete or not, or if it's a full, I'm sorry, if it's a full tree or not. Okay, the full and complete are confusing because what some people call full is what some people call complete. There's 2 ideas here. One is that one idea would be that every node either has 2 children or no children. Every node has either 2 children or no children. That's one of them. And then the other one is that the tree has 2 to the n leaves, where n is the depth of the tree. So let's call this one full and call the other one complete. So it's kind of iffy which one you call full and which one you call complete. It's a little bit tricky because they're very similar, but not quite exactly the same thing. Okay, so let's call this one full, okay, but not complete. Okay, so full means every node has either 2 children or 0 children. It either has 2 children like this one or 0 children like that. So every node is either a leaf node or it has 2 children. Okay, let's write a function that tells us if a tree is complete or not. Okay, or is full or not. So what I want to do is write a method. I'm going to call it, it's going to be a public Boolean. Okay, and I'll call it is full. Okay, so I want to write a method that determines if a tree is full or not. Okay, and it's going to be recursive because basically what you're going to do is say, you look at a node. If it has no children, it's full. So a node like this by itself, that's a full tree. Because remember, full is that every node is either no children or 2 children. So if the tree has no children, it's full. Okay, so that's actually the first thing we can write. Okay, if the left child is null and the right child is null, okay, that's our first case. Now this is not a recursive case. This is actually this is one of the steps that's going to stop the recursion. If we get to where we have a left null and a right null, then we actually are, it's a simple tree and we can return true. It's a single node tree, which is complete. Okay. Now we need another case. Well, what's the next case? Okay. Well, if you have one child, if you look like that, if you have a non-null left and a null right, so this is a non-null left and a null right, then you're not full. So if you're not null on the left and you are null on the right, okay, that means you are not. So that's going to be return false. So this is not a recursive case. See, this one's not recursive either. This is where we are not a full tree. But then there's a complementary version of this where the tree would look like this. That's not a full tree either. It's got a null left and a non-null right. So I can write that. I'll do a little copy and paste here. This would be or you're not null on the left and you are, oh, I forgot, let's see, which one, this should have been, this was not null on the right. So actually, which one did we do? The first picture, let's see which one we do. So this was not null on the left and null on the right. That's the first picture we did. And now we are null on the left and not null on the right. Okay. And if you want to group those carefully, so this is case 1. And then over here is the other case. Okay. Okay. So, oh, I'm editing the wrong line. I wasn't paying attention to what I was doing. It's hard to sometimes talk and write code at the same time. So this is the else if case. And this one was just that the two are both nulls. I got mixed up about what line I was on. Okay, if they're both null, return true. Else if one is null and one is not null, or the other one's null and the other one's not null, return false. Okay, those are two conditions that stop the recursion. Notice there's no recursion yet. Okay, so we've got the simple cases where it's either we know we either have a full tree with just a single node, or we have a non-full tree with depth 1, but one right branch and not enough left branch. Okay. Now we're in a case where we have, now this is just going to be else. There's a third case left. Okay. If you think about the cases we've done, okay, we've done that case. There's case 1. Okay. A tree with no children. Okay. Then we did the case of a left child or only a right child. Okay. So we did this case first, no children. Then we did this case. Now what's left is a case where, I'll draw it like this. Now we're left with a root with 2 children, a child to this side, and a child to this side. So now we're in this third case. We have 2 children. So this part is full, but we need to ask, now we have to ask this tree, are you full? Are you a full tree? And are you a full tree over here? Because if this one's full and this one's full, then the whole thing is full. Okay, so now we've got to the recursive part where we're like, it's like if in this picture here, this guy, he is full. He's this case here. So he asks this one, are you a full tree? And it is. And he asks this one, are you a full tree? And it is, because it's this one turns out to be that case there. This one is a recursive case of this one here. This guy's got 2 trees. So this one asks this, 2 asks 3, are you a full tree? Which will say, yes, it is. And then 2 will ask 4, are you a full tree? Okay. So a lot of times the way people draw a picture like this is, if you look in a lot of books, they put a little like they put a little triangle down here to represent that there's a tree down here and a tree down here. Okay, so they just, oh, I'm sorry, I used the wrong triangle. But a lot of books would draw this picture like this. The recursive case is a root with 2 branches and some tree here and some tree here. So this is to represent the idea. This is the recursion. That this is the case where we, and over here even I could have put a tree here, because this would still be false case if there's no branch here, and it doesn't matter what there is down here. So I could have put anything there. I could have put like a triangle to represent anything there to say that, well, if a node has a left branch and no right branch, it's not a full tree. Yeah. So I could have put a triangle here to represent the fact that it doesn't really matter what's down here. If this node has a left branch and no right branch, it's not full. Okay, so now I've got the recursive part. To ask if this tree is full or not, it's from the point of view of this node here, yes, it is full. So it asks if this is full, and it asks if this is full. So down here we would say return. Okay, I can write. The answer is left dot is full and right dot is full. Okay, that's all I have to do. I just return the anding of whether the left is full and the right is full. okay? And then that would be my recursion. The recursive function is going to call itself. If you look, there's lots of little different patterns in here. Here the recursion is in one if statement, and this recursion is in a different if statement. Here, both the recursions are in a single else clause. Okay, over here, this recursion was in an if statement, this recursion was in an if statement. Here, this recursion is in an if statement, and this recursion is in an if statement. Here it worked out. Now, what it was here is I was saying if there's a left branch, call this function recursively. And if there's a right branch, call this function recursively. Here the logic worked out a little different. If there were no branches at all, I have true. If there's one branch but not the other branch, I return false. So this else is, I know here that there are two branches. Okay, so I know here that there's two branches. So I can just call if is full on the left and call is full on the right. And I want to know, are they both full? They both have to be full for the whole tree to be full. Okay, so recursion, you have every recursion problem has its own little logic to it. Recursion just says that you're using recursion if a function calls itself. And it can be a little bit tricky to figure out exactly how you're going to use it. Whether you call the recursion, in separate if statements. Sometimes you recall the recursions like here, it's just one line does both of the recursions on the left and the right. In the toString one, it was similar to the other ones. If there's a left branch, recurse on it. If there's a right branch, recurse on it. So that's pretty common, but not all the time. See, here it was because of the logic that by the time we got to the recursion part, we know there is a left branch and there is a right branch, and we want the result of recursing on both of them. Now we should test this, okay? Well, first I can just compile it, make sure it compiles. Okay, so I didn't do any syntax errors in compiling the B tree. Now I want to test this program. So I want to show you a little bit about how we would test it. Okay, so I've got like this program. Here's a bunch of strings. Okay, so it might be let's find out which one of these is a full tree. Okay, so what I'll do is I'll just add to each of these cases. See, what I was doing is I'm iterating through these strings, and I'm building. First, I build the tree, then I print it, then I print it again as a B. Here I print it in one line, and here it's pretty printed. So let's just do something like this. Let's say system.out.println is full equal, and then I would say B tree dot is full. Okay, and you can kind of see this one's got no empty branches in it. 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 Oh, all of these are full trees. I thought one of them was going to be, I thought one of these had an empty branch in it somewhere. Well, I'll add one late in a minute. So all of these, so there's no empty branches in any of these trees. So they should all end up being full. So compile it. Whoop, now let's see, what did I do wrong? Oh, I forgot the closing parentheses from the printf, from the print line, okay? And run it. Okay, this tree is full, is full, is full. Okay, so there weren't any examples of a non-full tree there. So let me add an example. Okay, so let me add to this list of examples. Okay, now notice what I'm doing here is I'm using I can write my examples real easily here because I'm using the tree string notation. Yeah, I'm using this simple string notation for trees. So here's a tree, A with a left branch of B and a right branch, and B's left branch is C, and B's right branch is D. And let me give A a right child that is an E with an empty left branch and a right branch. Okay, so now I've created a tree that's not full because I put an empty branch into there. Okay, so I've added a string to this list. So this is a tree. A is the root. There's A's left branch. There's A's right branch. Okay, actually, there's A's right branch. Okay, A's left branch is full, but A's right branch has an empty tree. Okay, so compile it, run it. Oh, I see. I goofed up that string. Notice I got a error in the string. Oh, I forgot to put spaces here. Put a space there. Have to separate this. I have to separate all the symbols. Okay. Now that tree's full. See, is full is false on that tree because it's got this one empty branch there. Okay. Now let me do some other test cases. Okay. Real simple. That tree, there's a simple tree. That's our first case in the recursion. That's a tree that was a tree that was in this branch here. That was a tree that has a left and a right null, left and right branches that are null. So that's testing this case here. Okay. Now, what about another example? A with a empty left child and a right child. That tests the second case. And this also tests the second case. Okay. This one's full. This one's not full, and it tests the second case. This one's also not full, and it tests the second case. Okay. And then here's a simple test of the case of full, another A with B and C. Okay. So these four test this case here, the two possible ways you can be in this case here, and this case here. So there's four simple tests of those cases. Oh, and I goofed up typing in something. Oh, I keep forgetting. I have to put spaces around these guys. We'll talk a little bit about why that's the case. I need to put you notice that everything has to have a space around it. So every symbol has to have a space before and after it. That's just.
I think you accidentally deleted a line.
Pardon me?
I think you accidentally deleted a line.
Oh, I did? Let's see. Oh, you're right. Yeah, I accidentally deleted a line. Yeah, there. Okay, so there's the test case for a full tree. There's the two test cases for not full trees. And there's the simple test case, another simple test case for a full tree. Okay. True, false, false, true. Okay. So there's those test cases. Okay. Now, let me show you something that's a little bit interesting. Let me show you another way to, like, when you write code, you want to test it. And of course, one way to test it is to write a program to test it. This is kind of a nice permanent way to have your test cases. But let me show you something that's kind of a fun way to test your code. Okay. Here's the folder that has my code in it. Okay, let me clean it up. And okay, let me open a command prompt here, and I'm going to work with the command line for a little bit. So there's a command prompt in this folder. Okay. I want to compile the B tree program. So Java compile B tree. Okay, so I compiled my program. Now I want to run it. Okay, but I'm going to run it in kind of an unusual way. I'm going to start. Java now comes with an interpreter. It's called JShell. Remember, these guys are called shells. When you type commands, you call them shells. So this is the CMD shell. On Linux, you have the bash shell. Well, Java has its own shell that lets you type Java code. You have to be running Java 11 at least to be able to do this. Okay, now I'm in a shell that is Java code. Okay, so for example, I can do the following. I can say B tree, oops, B equals new B tree. I'm going to create a B tree. Oh, what did I? Oh, let's see. Oh, it's in the same folder. I'm trying to remember now how to use the my memory. I thought that the J shell would recognize what's in my current folder. Oh, darn it. Did I spell it right? You know. You see. No, that's not in a package, so I can't import it. Huh. Boy, I haven't done this in a while. It's been a while since I played around with the Java shell, and now I'm forgetting how to get it to use the files that are in this folder. Huh. Let me do something different. Okay, here's Dr. Java. Okay. I'm going to delete that class file, open B tree in Dr. Java, compile it. Dr. Java gives you a shell also. See this window here? This is the Java shell. Now here I can just say, see, that worked. B is a tree. Okay. I can't remember why it's not working. See, I can't remember what I'm doing wrong over here in the J shell itself. See, Dr. Java, I compiled this B tree, and I can just use it in the shell now. So here's an example of what I can do. I can say new B tree. I want this B tree. I'm sorry. We have this program that builds B trees for us. Where is it? Build B tree. So I'm going to open that program and compile it also. Okay. Then I can go over here and I can build a tree. So I can say build tree dot build tree. So there's a static method in that file called build tree. There's a static method in this file here that builds trees for us. And it takes as its input the string like the tree A with left branch B and right branch C. Okay. Oh, build B tree. I'm sorry. Build B tree. And then it's build B tree again. There. Oh. Did I
You
misspell
have
it?
built instead of build.
Oh, I'm misspelling it. Yeah. Build. Okay. And now I'm making that mistake of forgetting to space things out. There. All right. See, I just built a tree. Okay. And I can build another tree. I'll make this C with D and E. Okay. So now I have a tree. A is the root. B is its left branch. And A's right branch is a tree C with branches D and E. Okay. See. And then I can go here and I can ask that tree is full. True. Okay. And I can make it not full by putting an empty branch there. See, false. So notice how I can test my code in a command prompt. I have to figure out what's going wrong, why I can't do it over here. I'm not sure what I did wrong over here. I should be able to just take this line of code, copy it, and paste it over here too. But it's not finding the build tree. It's not finding these symbols. It's got to do with packages and things like that. Now over here, I'm not using a package name. So I'm in what's called a default package. So I'm working in Dr. Java in what's called a default package. And that's what Dr. Java does. If I don't give it a package name, I'm working in a default package. I thought the J shell worked with a default package normally, but I'm not sure what I'm forgetting. Trying to remember if there's some trick to get, if I need to do something to tell J shell to use the default package.
In PowerShell, you have to import modules if you need additional code. Do you have to import the class in the JShell?
I can't because it's not in a package. See, that's what I try. You can't import something that's in the default package. See, and that's if I could try putting it in a package, but I don't really want to put it in a package because notice I don't need it to be in a package. And Dr. Java doesn't need it to be in a package. When I'm working in TextPad, see, I can just compile this. Tools, compile Java. See, it doesn't need to be in a package. Now, over here in J shell, I could import things like I'll show you a little example. Okay, suppose I want to create a color object. So color C. Created variable C, however, it cannot be referenced until class color is declared. I never told it what color is. So if I want to actually do this, I do AWT, or I can say import AWT dot, no, I'm sorry, import java.awt see, I imported the color class. Okay, now I can say C is now, and I can say color C2 equals color dot red. Okay, so I imported something, but that's in a package. The color class is in the java.awt package. My B tree code is not in a package. Well, it's in a package. It's in what's called the default package, which is an unnamed package. Okay, so it's Java's unnamed package, which has actually got the name, the default package, but you can't import it. So the question is, how do you tell J shell to use the default package? And I thought it would do it automatically, and I really thought that it did it automatically. Anybody?
Can you paste the object class code into the shell and then run it? Because in PowerShell,
Yeah,
when I
you
run
probably.
scripts,
Boy, the trouble is it's such a long class, but you could, yeah, well, go like that. Let's see. Let's go to the. Okay, public class B tree. Copy it. I don't know. See, paste it. Create a class B tree. Okay, it probably is going to work now. Let's see if it works now. Now, yeah, see, it let me. Yeah, yeah. That's a really lousy way for it to work. That's a real. Oh, I think I know a better way now. Oh, now I remember what to do. Instead of copying and paste it, what I really want to do is I want to tell it to read that file in. So I think, let's see if it's the read. Oh, yeah. So that's the right idea. I want to tell JShell what classes I'm using, and it won't just read them out of this folder. But if I could, like, this is the kind of a crummy way to do it by cutting and pasting them. But there actually is a command. /help for help. Maybe it says open. Let's try open. So open /open build B tree. Was that spelled right now? Oh, .java. Probably needs the dot. There. Okay. Now let's see if I can do. Let's see if I can do this line now here. Nah, see, I opened it. Do I have to compile it too? When we copied and pasted this guy in, it said created class. But when we opened the file, it didn't say that it had created the class. We just didn't get any response. Do I have to do something else besides open it? Huh. Yeah, it's opened the file. It has it. So, but it hasn't compiled it yet, it seems. Now, when we copied and pasted it in, it seems that it created the class. See, it create. No, I'll have to go back. I'll have to go figure this out. It's been a while since I played with the J shell. Usually, I mean, a lot of times I would, if I want to play with the J shell, I just use it Dr. Java, because Dr. Java naturally gives you this shell right here. So Dr. Java makes it real easy to do this. See, Dr. Java makes it real easy to do this. So I can just type lines of code and test things. Okay? So I can build a tree like that, and immediately after the tree is built, I can call is full on that tree and get my answer here. Okay, so I build the tree with that string and then call is full right away. And this is a real nice way to test your code in a shell. That's why they invented that's why they finally added a shell to Java. Dr. Java's had this shell for years, long before Java had a shell. Dr. Java had a shell. That was actually one of the Dr. Java selling points, was that years ago, before Java had a shell, Dr. Java, they called it the interactions pane. They wrote the code to create a shell for Java. Okay, so they wrote their own shell for Java. And finally, the people who maintained Java were convinced to add a shell to Java. So they created the J shell. Okay, and if you, yeah, it's part of, I'll quit this. Let's see, what's the quit command? Oh, run. I just, yeah, that wasn't what I wanted. Yeah, the question is how do you get J shell to compile a file for you so you could use it in the J shell? I thought it was enough to just have it compiled ahead of time. I thought that if you compiled it ahead of time, if the class file was in this folder, J shell would see the class file and use it for you. But it doesn't seem to be quite working that way. Yeah, even though we loaded B tree, we build B tree, build tree's been compiled here, it's still, the J shell still not seeing it. What? Okay, let's try one last thing. The dumb thing to do is just, okay, wow, it's still, did I mistype something? Oh, B tree uses tokenizer, so I have to keep loading class after class into this thing. See, okay, maybe. So I had to, yeah, I don't, this seems kind of dumb that you would have to load all these classes by hand. There's got to be a better way. Let's see if it finally works. Yeah, see, it finally worked. Yeah, so, okay, so the dumb way to do this is to load the classes, just paste them in one at a time. But there's got to be a better way. There's got to be a better, now, Dr. Java didn't, see, notice I didn't even need to have tokenizer loaded here, because when I built B tree, if I go over here and I delete that class file, delete that class file, delete that class file. And then if I just if I build, okay, I can even close this one. If I build this guy, see, Dr. Java built that one because this file depends on btree, so btree gets compiled. This file depends on tokenizer, so tokenizer gets compiled, okay? So everything gets compiled automatically. I only have to compile that one file. And but the J shell seems to be kind of weird. I mean, it works if I load every class into it one by one. That's not convenient. There ought to be a way. There ought to be a way to just sort of type a command here that says I'm going to use all these classes. Notice that everything's. I'm not using packages though. Everything is still in the default package. So I'm not. I can't import them because you cannot import something that's in the default package. So there's got to be a way to tell JShell that I want to use that file, and that file without having to import them. You know, and it didn't seem to work even when I did the where was it? The open didn't seem to do it. That opened the file, but it didn't seem to compile it. It can't be import, and I'm not sure. I don't, you know, I don't know if I should have, but you notice that there's a reload, but there's no load. But maybe it is. Let's try one last time. Let me just quit this. Okay, so I'm out of it. Now I'll just open it back up again. Let's just try. I don't think there's. Let's see. Is there a load command? Load btree.java. No, there's no load command. Try reload. Yeah, I'm not sure what went wrong there. Okay, so I have to, okay. Using a shell is a real good way to test code and to play around. The J shell is kind of new. I haven't been using it that much. Yeah, like I say, I usually just use Dr. Java. When I wanted a Java shell, I tended to go to Dr. Java and just use it. But it's kind of nice to maybe start learning how to use J shell too. So I do have some documentation on it. Last night I didn't sit down and read it. I probably should have read the documentation on J shell before. Okay, there's some good articles on the internet that explain how to use J shell. Okay, but the whole point of it is to be able to test your code, like, you know, just like Dr. Java has this shell. The idea is that a shell is a real convenient way to test your program. So you can just type in a couple of lines and see things work and try them out. Okay. Now let's go back and, okay, let's quit this and quit this. Let's look at more recursive functions in the trees. Let's look at more examples of recursive tree functions. We want to look at, in the reading assignment, if you go back here, one of the first reading assignments was this section on B trees in this book here. And it starts with this idea of tree traversals. Okay, so what do we mean by a tree traversal? A tree traversal is a way to, now, like, you know what it means to traverse a list or traverse an array. You start at the beginning and go to the end. Okay. Lists and arrays are linear. So it's real easy to say how to start at the beginning and go to the end. But a tree is not linear. What do you mean by saying you want to traverse a tree? You want to start at the beginning. Well, here's the beginning. And then you want to go to the end. Well, notice that there's lots of ends. There's 3 leaf nodes here. So what do you mean by traverse a tree when you mean, you know, it's clear what you mean by start at the beginning. You're going to start there. But it's not so obvious what you mean by go to the end of the tree. Okay, so there are multiple ways to traverse a tree. In fact, there's 3 ways. If it's a binary tree, there's 3 ways to traverse it. Actually, no, there's actually more than 3 ways. There's there's a lot of ways to traverse a tree. Okay, so we'll go through, let's go through several of them. Okay, I can think of, for a binary tree, I can think of 4 ways to traverse the tree. Okay, one way to traverse the trees, they all start at the root. Okay, but then the question is, what do you do after you visit? Okay, so you start with the root. Where do you go next? Well, you can go left. Okay, so that's next. Then you're there. Then you can go left again, but now there's no left, so you go back up. Now you haven't gone right yet, so then you go right. Okay, now you're here. Now you're done. So you go back. You're done here because you've done all of this. So you go back here, and you haven't done right here. So now you go here. Now there's no left branch here, so now you go here. There's no left or right branch, so you go back here, you go back here, you're back where you started, so you're done. Okay, that's the rough idea of what a tree traversal is. Okay, you start at the root, you go left, then you go left, then you go back to the parent, then you go right, then you go back to the parent, and you're done. Go back to the parent, go right. There's no left, go right. There's no left, there's no right, go back to the parent, go back to the parent. Okay. Now, the traversal I just gave you there is a little bit ambiguous. There's a notion of, when do I visit this node here? So there's this idea of what we call visiting the node. When I start here, I could, suppose I want to print the numbers that are in this tree. Okay, so the numbers are 1, 2, 3, 4, 5, 6. When I start here, should I print that number right away, or should I go and do this side of the tree first? So for example, I could print this number, then do the right side of the tree, do the left side of the tree, then do the right side of the tree. I could also, when I get to this node, say, go do the left side of the tree, then when you're back here, then print 1, then do the right side of the tree. Another possibility is I can say, I start here and I say, do everything on the left, do everything on the right, then print this thing last. Okay, those gives you 3 different traversals of this tree called pre-order, in-order, and post-order traversal. The idea is, when do you print, or the more general term is, when do you process this node? Do you process this node before the left and the right branch? Do you process this node in between doing the left branch and doing the right branch? Or do you process this node after doing the left and the right branch? That's called pre, in, and post-order traversals of this tree. Okay, and those are recursive, because what it boils down to is, how do I do, okay, let's say I want to do a pre-order traversal. So that means I get here, I print that node, then I traverse this. So then that's the recursion part. I then just do a pre-order traversal of this left branch. Then when that's done, then I just say, do a pre-order traversal of the right branch. So the way I do a pre-order traversal of this tree is, print this node, pre-order left, pre-order right. The way I do an in-order traversal of this tree is, I start here, and I say, okay, first thing is do an in-order traversal of the left branch. Then when that's done, I print this. Then I do an in-order traversal of the right branch. Okay, and the way I do a post-order traversal of this tree is, I start here, then the first thing I do is a post-order traversal of this recursively. Then when it's done, I do a post-order traversal of this. Then when it's done, then I print this guy. So that gives me 3 different traversals: pre-order, in-order, and post-order traversal. Now, another kind of traversal of this tree is something called in-order traversal, which is a little bit more complicated. And the code for it is not in here, but the traversal order in that case is, do the top level, then do the nodes in the second level, then do the nodes in the third level. So that traversal would go 1, 2, 3, 4, 5, 6. That's sometimes called a level order traversal, or a breadth first search traversal. Okay, so it's called level order traversal or breadth first traversal because you go across the breadth of a level before you go across the breadth of the next level. So it's referred to as breadth order traversal or level order traversal. That's a more complicated traversal. It's not described here, but that's another one. Notice that would give you 1, 2, 3, 4, 5, 6. Now, what does in order traversal give you? In order traversal says do the left branch, then print this, then do the right branch. So what would this thing print out? Okay, in order traversal would say, oh, I have to do the left branch first. Then I get over here. In order traversal says I have to do the left branch first. Now I have to do level in order traversal here. There is no left branch, so I print 4. There's no right branch. I'm done with this guy. So then I go up here. Now I'm in the middle of this, so I can print the 2. So now I've printed 4, 2. Now I've done the middle part of this, and I can do the right branch of this guy. This guy has no left branch, so he prints a 5, and he has no right branch, so he's done. So now this guy is done. Now we've printed 4, 2, 5 in that order at this point. Now we're finished here, so now we go to here. Well, we've done the left branch, so in order, we print 1. Okay, so now we've printed 4, 2, 5, 1. 4, 2, 5, 1. And now we're ready to do the in order traversal of this guy. So this guy does his left branch first, but there's nothing to print. So then it prints 3 in the middle part. Then it does its right branch. Its right branch has no left branch, prints 6, no right branch. So the in order traversal of this tree would print 4, 2, 5, 1, 3, 6. 4, 2, 5, 1, 3, 6. Notice that that's kind of like going from left to right, but keeping track of, see, this one is to the right of that one. This one you think of as to the left of this guy here. So you think of this whole tree here as to the left of this one. So if you read across from left to right, it'd be 4, 2, 5, 1, 3, 6. That's the in order traversal. Okay. Now, actually, the code for that is over here. Here's the in order traversal. It takes in a B tree, and it's going to traverse it in order. It's going to print out a string, so it starts off with an empty string. And what it does is it says, if there's a left branch, tack on to my result the in order traversal of the left branch. So if there's a left branch, do it. Do its in order traversal. There's the recursion. In order calls in order. Now, after you do the left branch, you tack on the element itself, the root. Okay, so we're adding on to this. So we start with an empty string. If there's a left branch, we add the left branch's in order traversal to our result string. Then we add the root of this tree. And then we add, if there's a right branch, we add on the in order traversal of the right tree. Okay, so that's all. It's just a few lines of code. If you get rid of the comments, it's just a few lines of code. Start off with an empty string, traverse the left branch, traverse the root, traverse the right branch, return the result. Okay. Now, pre-order traversal just reverses the order, changes the order of this stuff. The pre-order traversal starts off by saying, okay, I'm supposed to process the root first, then process the left branch, process the right branch. So process the root first. And post-order traversal does the left branch and the right branch first and does the root last. Okay, so post-order traversal, because the root is at the end of the recursion. In order traversal, because the root is in the middle between the two recursions. And pre-order traversal, because the root is before the recursive traversals. Okay. All right. Your homework assignment is to do a variation on pre-order traversal. Because when you want to print a tree, you usually want to print the root somehow before you print the left and the right branches. Okay. Now that's not always the case. if you think about this, the root, but see, this is, now this two-dimensional picture can't be done by a tree traversal. But if you notice that the left, in a sense, if you think of it as moving from left to right, the left comes first, then there's the root, then there's the right. So in a sense, this two-dimensional picture is kind of an in-order picture. The left stuff comes on the left, then the root is in the middle, then the right stuff's on the right. But when we print the string out on a terminal, we can't print it in a 2D way. Go back to this results here. See, when you want to print on a terminal, you have to print the root, then the left branch, then the right branch. Print the root, then the left branch, then the right branch. So this is in order traversal. When you print the tree, you're doing whenever you print the tree on a terminal, it's always going to be a pre-order traversal where somehow you print the root, then you print the left branch, then you print the right branch. Here it's all in one line. Here it's root on a line by itself. Here in this one, every node is on a line by itself. So there's the root, there's the left branch, but indented a little bit. Then there's the right branch indented a little bit. When you print A's left branch, you start off by printing his root, then you print his left branch indented and his right branch indented. Okay. This is a pre-order traversal because it does root, then left, then right. Here it does root, then left, then right. So it's a pre-order traversal where you're using a mixture of indentation and everything here is on a single line by itself. Here, everything's all on the same line. Your homework assignment is to compact this output. Let me show you what it looks like. Go to the homework assignment. Okay, this tree here is this one here that we've been working with. Okay. So this tree here is this one here. And this output is this one here. Okay, and this is written for you. So this, you have to write the traversal that does this output here. You have to do that one. You have to do 3 of them. That one, this one, and this one. Now, what did this one do here? What this one did is it said, see this tree here? It's a very simple tree. It's got depth 1. It's just B. It's B with children D and E. So why not just make that tree in line, kind of the way it's done right here? Since it's a simple tree, it doesn't need to be spread out over 4 lines. It could just be inline. We call it inlined. So when a tree is real simple, meaning it has depth 1, you just make that tree inline. Now here's another example of that. Here, G in this tree here, see, it's just G with a left and a right branch. G's left branch is empty and G's right branch has nothing in it but an H. So it gets inlined. Notice that makes the output a little bit easier to read. Okay, so you have to you have to modify this traversal, which is given to you, so that when it sees that a tree has depth 1, it just inlines it. When a tree has depth 1, it inlines it. Okay. Now here's another way to make this output simpler. Another way to make that output simpler is to always put a left child in line with its parent. Okay, so that would promote B up to in line with A, and that would take the D and put him in line with the B. Then it would take this guy and put him in line with the C. And it would take G and put him in line with the F. The output ends up looking like this, and it ends up being easier to read. It ends up looking like this. A has left branch B, which has left branch D. Okay, and then B's right branch is E. And then A's right branch is C, which has left branch empty, and C's right branch is F. But F has left branch G, which has empty left branch, and G's right branch is H. And F's right branch is empty. Okay, with a little bit of practice, you get used to reading these. Okay, so this is another way to make this kind of verbose output a little bit shorter. Okay, so you can inline degree 1 trees. You can inline left children. So I want you to do those two as separate examples. Then the third one is to combine those. This one inlines the left children and also inlines the tree of degree 1. Okay, so there's the tree of degree 1 inlined. There's the tree of degree 1 inline, but you also are inlining the left child. Okay, and also here, A's left child is this whole tree B. Okay, so this third pretty printer is a combination of the first pretty printer and the second one. The first one inlines trees of degree 1. The second one inlines left children. And then the third one just combines them. In fact, your third program will just be essentially, you either take this one and copy and paste some code from this one into this one, or you do it the other way around. You take some code from this one and copy and paste it into this one. You're just going to merge these two versions. Okay. Once you get this one working and you get this one working, you essentially just merge the two together to get this one. You won't have to write any new code. You just have to figure out how to merge the code from these two together. Okay. And these two, you can get them by thinking hard about how this one works and modifying it. In the folder for the homework, let me clean this up. Oh, I didn't download the folder yet. Here's the pretty printer that's given to you. That's the one that does this pretty printing. Okay, so that's been written. And it's the same one that's in the binary tree folder. Okay, so there's the basic pretty printer. Then you have to write this. Now see, this is empty. So this is where you put the code. This is where you would put the code to do the other pretty printing. So there's a pretty printer 1, which inlines trees of degree 1, pretty printer 2, which inlines left child, and then pretty printer 3, which merges these two together. When you're done, this program should compile and run and produce this output. And what this output does is it shows you that pretty printing, which is written for you, that pretty printing, which is written for you, and then your pretty printer 1, your pretty printer 2, and your pretty printer 3. And then it also just called the traversals. That's just to make sure that everything's built right. So the traversals are in there. You don't have to do anything with them. It just prints out the traversals just for you to kind of practice reading these. Okay. And then there's the second tree. There's one pretty printing that I gave you. There's another pretty printing that I gave you. And then you have to do this one, which compacts inline, degree 1 trees get inlined. Then this one, which inlines left child with the right. Yeah, you always puts the left child in line with the root. Always puts the left child in line with the root. Always puts the left child in line with the root. And this one, which combines those two. Okay, so then the trees are going to be printed out 5 times because there's the 2 pretty printings that I gave you, and then there's the 3 pretty printings that you have to write. Okay. All right. So that's the homework assignment. You're going to write recursive pretty printers based on this one. Yeah. You have to figure out what to do, how to modify this one to get the two. Well, you have to really get 2 pretty printers, and then you're going to merge them together. So you have to modify this one to get 2 new pretty printers, and then you get a third one kind of for free by merging the other 2 pretty printers. Okay. So you're going to write a pretty simple recursive. You're not going to write much code. Notice that this is just, the guts here is only like 10 or 15 lines. you're going to only add like 7 or 8 lines of code to these pretty printers. You're not going to have to write a lot, but you have to think a little bit. Yeah, you have to think about where you're going to put the code. Yeah, start with this idea here. You could just try modifying this one instead of, if you want, you can just ditch this. You might think, how would you modify this one to make it do the first of the new pretty printers? So you can either copy and paste this one into here or however you want to do it. But make sure you understand this pretty printer. And the other pretty printer is the toString method in the B tree itself, which is actually also a pretty printer. The toString method in B tree is a simple pretty printer, and it does everything in line. It does everything in line. So you might want to look at this one too, because this one just does everything in line. Okay, so there's one pretty printer. There's another pretty printer, and then you have to write this one. Okay. All right. Okay, we've got to the end. Okay. Make sure you read the description of tree traversals here. And also, if you're not comfortable with recursion, there are more examples of recursion in this book. There's a section here on recursion. Yeah. Okay. So you might want to read. It's not about trees or anything. This is just recursion in general. So there's a little bit of discussion here of recursion. If you have your data structures book from last year, there's a chapter on recursion in the data structures book that's pretty good, that's worth reading. And if you have questions, please send me emails or come to office hours. So if you have questions about this stuff, please ask. Okay. But we're going to use a lot of recursion this semester. Recursion, when you work with programming languages, recursion, even languages that don't have recursion in the language, programming languages are inherently recursive. We'll see what I mean by that as we go along, but you can't talk about programming languages without talking about recursion. So we're going to use a lot of recursion as we go along through the semester. Anybody got any last minute questions? Anything that come up that I didn't say anything about? Anything you want to ask about? Okay, yeah. So the homework assignment's due in 2 weeks, 2 weeks from today. Okay, and yeah, if you have any questions at all, please send me emails and things, or come to office hours. Okay, so we've gone over a little bit, so I'm going to go ahead and stop sharing, and we'll meet again on Thursday. Okay, bye-bye.